Okay, so we are now going to solve the exercises of this last section on sequences. I forgot about these exercises. I thought that the chapter is over. Anyway, so let us first go through this one, which we are supplying. I mean, we have made this exercise. It will complete the proof of lemma 671. Let us recall what we had in lemma 671. What we had there is a positive real number x and a sequence of rational numbers that is convergent. We were then required to prove that this sequence is also convergent. Additionally, if this is another sequence of rational numbers that is also convergent and these two sequences have the same limit, then we were required to prove that that corresponding to sequences involving powers of x with these exponents also, of course, they are convergent. That follows from the first part of this lemma. But these two corresponding sequences converge to the same limit, same real number. Now, we have already seen the proof of this lemma. We mentioned that the case x equal to 1 is trivial, because in that case this sequence will be the constant sequence one, and in that case we have already seen that the conclusions are true. And in the text we have seen the proof when x is greater than 1, and completing the proof, that means requires us to show that the conclusions are also true when x is less than 1. So that's what we are going to do here. So we start by assuming just that. Okay. Since we have already proved the lemma, in the case where x is greater than 1, the limit L exists, which is this limit 1 over x to the power qn, which is also this. This limit exists. Why? Because x is less than 1, so 1 over x is a real number greater than 1. So by what we have already proved in the text, this limit exists. That is, we have written here the conclusion where in place of x we have 1 over x, which is greater than 1. So we have been able to conclude that this limit exists. Now our aim is to now show that this limit L is not equal to 0, and this we will do by supposing that L is 0 and then getting a contradiction. So suppose L is equal to 0. Now let us, before we do anything else, let us think for a moment, how can L possibly be 0? You see one thing, that the exponents of course are being rational and with no other restriction. The exponents each qn can be positive or 0 or negative, that thing is there. But these powers x to the power qn, these are always positive. Okay, and that is coming from that lemma 569 part A. We have already proved that thing. So these reciprocals are also positive. That means this sequence whose nth term is 1 over x to the power qn is a sequence of positive real numbers. But still there is a possibility of having a 0 limit. One such sequence is this sequence, the sequence of the reciprocals of the positive integers, where all the terms are positive real numbers, in fact rational numbers, but the limit is 0. So just from here we cannot immediately conclude that the limit is non-zero. The limit can be 0, but the limit cannot be negative. That thing is there. Okay, so we have now supposed that the limit is 0. Now what can we do from here? Let us see. Because the limit is 0, then for each positive integer n, or let us write like this, for any positive integer n, there exists a positive integer k. Such that these inequalities are true. X to the power minus qn this is less than or equal to x to the power n for all n greater than or equal to k. Okay, will it be okay if I use some more ink, because I don't think it's quite visible. Now what have we done here in this line? Because L is the limit of the sequence 1 over x to the power qn, so what we have done here is nothing but we have applied the definition of limit. Our epsilon is x to the power n. Our limit, of course, L is according to our supposition 0. So the distance between the nth term of this sequence, which is nothing but x to the power minus qn, and 0, the limit, this distance can be made as small as we want. How small? This small, less than or equal to this, and that will happen from some stage onwards. That stage is k, and this n is also our choice. I mean, first we choose any positive integer n, then for that n there exists such a stage such that this thing will happen. So that means for each n there is a k, and this absolute value is of course equal to this. This, however, is equal to this without any absolute value. That is because any such power itself is a positive real number. We have already seen this in lemma 569, part A, I think. So that's how we are getting this line. Now, what is the implication of these inequalities? From this, we can conclude something about and the fact that this x to the power n is itself a positive real number comes from, let us mention that, see lemma 569 part A. This implies we are going to write something, and that will follow from again lemma 569, but this time part E. That the exponent minus qn is greater than or equal to n for all n greater than or equal to k. That is, this thing is coming from this inequality. X to the power minus qn is less than or equal to x to the power capital N. That implies that this exponent is greater than or equal to, the inequality gets reversed, capital N, and that is because our base x is less than 1, and this fact follows from this part E of lemma 569. So now you see one thing. Now, what can one say from these inequalities, these things that we have, the latest things? It is that for any choice of capital N, there exists at least one minus qn that is greater than or equal to that capital N. In particular, minus q capital K is greater than or equal to capital N. So no matter what n you choose, no matter how large this positive integer n you choose, you will get at least one minus qk that is greater than or equal to that integer. So the sequence minus qn is not bounded above. It has no upper bound, and as such it is not bounded in general. That is the conclusion. So we are of course going to write it in one line only. Thus, the sequence minus qn is not bounded. But we know that the sequence qn is convergent. Is convergent, and so by the limit laws the sequence minus qn is also convergent. In fact, its limit will be the negative of the limit of qn, whatever it turns out to be. Is also convergent and hence bounded. This is something we already know. We have proved that any convergent sequence of real numbers is bounded. So this now we have arrived at a contradiction. This is not bounded and simultaneously bounded. This is a contradiction and proves that our supposition is wrong, that is L cannot be 0. Have we made any more assumption here? I mean, right after this supposition we haven't assumed anything else, no? There is no more case. This is all we have. So yes, that implies that the supposition is false. And shows that our supposition is wrong. Hence, by the limit clause, which also is theorem 6119, this limit exists. Limit of x to the power qn exists and is equal to 1 over L. That is the first half of lemma 671 in this case where x is less than 1. We want to prove that this limit exists and the limit of the sequence, which is obtained by taking the reciprocals of these terms, that limit is L, and that exists, that we have obtained from whatever we already proved in the text of lemma 671, our lemma. And so now the additional information that we needed in order to be able to use this theorem is the fact that that limit L is non-zero, so that you can take the reciprocal of this. You see, the terms themselves are of course non-zero, that we already have, but the limit, there was a possibility that the limit could be 0. Now we have seen it's non-zero, so we are able to use theorem 6119, that part of this theorem which gives you this, that if you have a sequence of real numbers that converges to A, all the terms of the sequence are non-zero real numbers and the limit is also non-zero, then this sequence is also convergent and it converges to 1 over A. That's what we have used here. So now we know that even in the case x less than 1, this sequence whose nth term is x to the power qn, that is still convergent, like what we had in the case x greater than 1. But there is that second part also, which asks us to show that x to the power qn prime also would converge to the same limit, and that now will come like this. By what we have already proved in the text. In the lemma does not make sense. In the lemma means what? In the text of the lemma, we have limit of x to the power qn, or okay, instead of doing it directly, let us consider this. This is equal to this limit, and which of course is equal to this. For these equalities, we did not need this thing what we have done here. We could have started with this one also, because our base now is 1 over x, which is greater than 1, and for such bases we have already proved the lemma. So the uniqueness comes from here, comes from that proof, and we have written like this. And this common limit, which we know is L, and that is non-zero. From that part onwards, we need what we have proved here. Non-zeroness of L has been proved here. Since this limit, you can write, this is Qn prime within bracket, which is L, is non-zero it follows from again the limit laws, theorem 6.1.19. That limit of x to the power qn as n approaches infinity is equal to the limit of x to the power qn prime as n approaches infinity. This now completes the proof of lemma 671 in its entirety. Yeah, that's just it. Now let us see the sole exercise of this section. Prove the remaining components of proposition 673. Yes. Okay. So that means we have to first recall the statement of proposition 673. We will do that here. We need to retain the statement for some time. I mean, at least until the proof is over, the solution is over. So we will write the statement briefly there on the top of this left hand side, and we will keep it. So that means here we have two positive real numbers x and y, and any two real numbers q and r. X and y are positive real numbers, which I am writing extremely loosely like this, and q and r are any real numbers. Part A says that any power of x, x to the power q, is positive. Part B, of course, is those familiar rules of exponents. There are two of them, of which we have already proved one in the text. This is one, this is the one we have already proved in the text, and there is this other one. Then part C is something like this: x to the power minus q is 1 over x to the power q. Part D, parts D and E, they involve inequalities involving powers. Q is given to be positive. Note that this is an extra condition, extra hypothesis. Then x is greater than y if and only if x to the power q is greater than y to the power q. This is D, and this is then these two inequalities are equivalent. If one happens, then so does the other. In part E, there are two parts depending on the type of the base. If the base is greater than 1, then here the base does not change. Here the base, we have two possibly different, of course possibly different means different bases. In this one the base will stay the same, but the exponents will change. If x is greater than 1, then x to the power q is greater than x to the power r if and only if q is greater than r. This is one thing. And if x is less than 1, then this if and only if, this time the inequality will get reversed. Q is less than r. We need to prove these things, among which we have already proved only this. The rest we now have to do. So let us start with the hypothesis. The hypothesis is that x and y are real numbers, and these are also real numbers, but x and y are positive. So because q and r are real numbers, by the definition of real numbers, each one of them is a limit of a sequence of rational numbers. So we start by assuming just that. Let Qn and Rn be sequences of rational numbers converging to Q and R respectively. This solution is going to be somewhat technically heavy, so I should be careful, more careful than usual. Okay, now we start solving part A. So in part A we have to prove that this power is positive, x to the power q is positive. Okay, so we take the help of Lemma 569, which deals with precisely these things, but where the exponents q and r are rational numbers. Since by Lemma 569a we cannot do anything with this part. Okay, we have to use only this much space. Since by this first part of Lemma 569, x to the power qn is greater than 0 for all n greater than or equal to 1, we have but by what? By the comparison principle and proposition 6. Okay, by, it's difficult to keep track of so many and proposition. I will say what these two things ultimately are telling us together. We have x to the power q greater than or equal to 0. This is Lemma 6413 is the comparison principle, which if you recall is something like this. Now, there are two sequences of real numbers an and bn where the nth terms behave like this. Okay, they are related like this of the two sequences. Then the comparison principle says that let's say we consider the limit superiors. These two limit superiors also are related to each other by such an inequality. Now, if your original sequences are themselves convergent, then by proposition 6 for 12 part F, this is the last part, we know that these limit superiors are actually limits equal to limits. So this is what we have used here. How is that coming, or exactly how are we using this? That sequence an, in its place we have x to the power qn, and in the place of the sequence bn we have the constant sequence 0. So we take limit on both sides, limit of the constant sequences, all of whose terms are equal to 0 is 0. But there is one thing, in the comparison principle, if you look carefully, we don't have strict inequality. Here, however, we do have strict inequality. I mean, we'll start with strict inequalities. These strict inequalities imply ordinary inequality. If you have strict inequality, that implies this, but this does not imply that strict inequality necessarily. So we can go from here to here, from here to here, and this thing is by definition x to the power q, that is greater than or equal to 0. So using all these results, we can say only this much, but we need this strict inequality. For that, now we have to work, we have to do more work. So the way things are going, what is more natural than to suppose that this is 0 and then derive a contradiction? So that's what we will do. Suppose x to the power q is actually equal to 0, then for any positive integer you will see that some arguments are similar. Going through this type of arguments, you will get an idea of a rough idea of what to do in a given situation. Although no one really knows what has to be done, and there is obviously no one way of doing anything in analysis. Most often there are multiple ways of approaching something. Integer n1, there exists a positive integer well, let me just take what I have taken here, otherwise I will confuse myself. K1 such that x to the power qn equal to the absolute value of x to the power qn, that is less than or equal to x to the power, are we taking n? Yes, n1. For all n greater than or equal to k1. Since we have seen an exact similar, almost the same thing before, so we know what we have done here. It is because this x to the power q is also a limit like that L, and that limit is 0. So for this epsilon, there is a stage starting from which onwards, that stage onwards, these inequalities are going to be true. And now you can understand what we are going to do next. But there are cases depending on what x is. We are no longer proving lemma 671, that is over. Okay, so now our x may be less, it is less than 1, maybe it is greater than 1, no one knows. So we first consider the case x less than 1. If x is less than 1, then qn will be greater than or equal to n1, because the base x is less than 1, and here we are again using that lemma 569 part E, I think. You know what we are using here. Then Qn is greater than or equal to n1 for all n greater than or equal to q1. This implies our sequence Qn, so we don't have to do anything more here. We have got exactly the sequence Qn itself is not bounded. This is a contradiction, because we know that Qn is convergent and hence it has to be bounded. This is a contradiction. But there is one more case. If x is greater than or equal to 1, then if x is greater than or equal to 1, then these inequalities imply that, oh, then I think we will not deal with this at all. I mean, we will consider something else. So we will not start the line like this. So because of this contradiction, all we can now say is that x cannot be less than 1. So assume x is greater than or equal to 1. Again, because this limit is 0, no, this okay, this assumption does not directly say anything. We are again going to use this fact since, but now we are going to write something else in place of this. Since x to the power q, this limit is 0 for any positive integer n2, there exists a positive integer k2 such that this time x to the power qn equal to absolute value of x to the power qn is less than or equal to x to the power minus n2 for all n greater than or equal to k2. Note that just like here we chose this value of epsilon, this also can be chosen in place of epsilon, because although minus n2 is a negative integer, but the power x to the power minus n2 is a positive real number. So these inequalities are true, and they are true for n greater than or equal to k2. This implies okay, now the inequality will not get reversed. I mean, when we write an inequality for the exponents, those inequalities will not get reversed, they will be like this only. That is because our x is now the base is greater than or equal to 1, and this again is coming from that lemma 569 part E. So Qn is less than or equal to minus n2 for all n greater than or equal to k2, or minus Qn is greater than or equal to n2 for all n greater than or equal to k2. So the sequence minus Qn is unbounded, a contradiction like before. Why it is a contradiction, that we have already seen. So that means no matter what x is, whether it is less than 1 or greater than or equal to 1, we are getting a contradiction. So that means something is wrong, and that something is our supposition that the limit x to the power q is 0. So our supposition, this is wrong, but we have the fact that the limit, this limit is non-negative, greater than or equal to 0. So the only possibility is that it must be strictly greater than 0. So this is this proves part A. Now we go to part B, in which of course we will have this available to us from the text. We will prove this. However, we are going to now see parts B and C together, in which we will first prove C, and then using C and this part of B we will prove this for technical reasons. Because of the nature of this solution or this thing itself, I urge you to go through the steps carefully, and if you spot any mistake, please let me know. We will try to rectify it. So far I have seen many times, actually I haven't found any mistake. Okay, so instead of writing B, we write B and C. B first prove part C. Okay, so in part C we have to prove something like this. So how can one prove that? By part A, x to the power q is not equal to 0. Yeah, that we have already seen. I mean, it follows directly from part A that whatever q is and whatever x is positive of course, but whatever positive real number x is and whatever real number q is, this power is non-zero. In fact, it is positive. We need non-zeroness here. Then x to the power minus q is equal to x to the power minus q times 1. Now, because x to the power q is non-zero, 1 can be written as x to the power q times 1 over x to the power q. And now what we do, we take these two things together and apply part B, that part of part B that is available to us, that has already been proved. So because of that, we can write this power in place of this product times 1 over x to the power qn. This power is 1, that is by definition. So you see that part C is rather easy to establish. That is because we have already done the heavy work here. So we are reaping the benefit now. Within brackets we write, note that we have used the first identity of part B here, which has already been proved. So this is part C. Now we prove the second identity of part B. Okay, it will take we will need to do many things. But again I am saying, these proofs may look quite complicated and involved and somewhat long, but there may be some very smart and short proofs. If you find any such, you please let me know. The second identity of part B. But before that, we are going to prove something else which we will need in the course of this solution. We prove the following result. And what is that result? Let xn, where n varies from 1 to infinity, be a sequence of positive rational numbers that is convergent and has a positive limit. Be a convergent sequence of positive rational numbers such that the limit of this, which again we haven't used any L here in this proof. Okay, so the limit of this is positive, then for any rational number sigma, we have this limit xn to the power sigma equal to L to the power sigma. It looks somewhat like Lemma 671, but note that we are not just simply saying that this limit exists. That is something we already know. Now, what the hell am I saying? In Lemma 671, our base is fixed. Now, what I said just now is not the thing. Here the base is changing and the exponent is fixed. No, so this is something else entirely. Okay, see, I just misinterpreted this. Okay, and in proving this, we are again going to use something else, which however we know from elementary algebra. In proving this, we shall use the fact that for any real numbers a and b and any positive integer k, you have something like this. Maybe you already know this from your elementary algebra courses, or one can prove this also very easily by induction on k. Okay, so let us now start showing this thing. How can we possibly proceed? We start by considering the fact that sigma is a rational number. Since sigma is rational, we have sigma equal to s divided by t, where s and t are integers and t of course can be conveniently chosen to be a positive integer. That we can always do. Okay. Now we are going to use the fact that this limit is actually a positive real number. Since L is greater than 0, we can choose a real number C such that C strictly lies between 0 and L. If you want to be specific, you can take, in place of C, you can take say L divided by 2 or L divided by 3. Those values will work. Okay, now we apply the fact that L is the limit of this sequence xn. Since L is the limit of xn, there exists a positive integer there exists a positive integer. It does not matter what we take, but let me just take what I have taken here. N such that C is less than xn for all n greater than or equal to n. Why? Because you see, the situation is like this. This is here 0, this is L, C is here somewhere. C may be very close to L, that does not matter. Because L is the limit of the sequence xn, you can find a region around L small enough to not contain C. Then because of the fact that L is the limit of xn, most of the sequence terms will be trapped within this region. Only finitely many may lie outside the region, will lie outside the region. So starting from some stage, and that stage here is n, all the terms xn are going to lie here. Okay, and so automatically for those terms, all of them are greater than C. And if you are wondering what this region is nothing but your open interval L minus epsilon, comma L plus epsilon for some suitably small epsilon, so that this does not contain C. Okay, so that is how we are getting this inequality. Right, so now what is the consequence of all these things? Now choose, let's just keep this figure, okay. To avoid confusion, let us take this to be epsilon prime, because we are now going to choose epsilon. Now choose epsilon to be a positive real number, any positive real number. Epsilon is not restricted in any way and is not related to any of the quantities we have seen so far. Then for this epsilon, there exists a positive integer. Again we are going to use the fact that L is the limit of the sequence xn, but in a different way than this one. There exists a positive integer k, this time we are taking, such that this I have to write carefully. The distance between xn and L is less than or equal to epsilon times c to the power t minus 1 divided by t plus L are we writing, no, L we are writing after c to the power t minus 2 divided by t times L to the power 1 over t plus etc. plus c to the power 1 over t times L to the power t minus 2 divided by t plus L to the power t minus 1 divided by t. It seems like no one knows why such an expression has to be chosen, but this of course you can guess. We have come up with this expression only from what we would later encounter. So this comes from back calculation. The point here, as of now, we only need to make sure that the right hand side is a positive real number. Let us complete the sentence. For all n greater than or equal to k. And this fact of course comes from the fact that L is the limit of xn. Now the positivity. Recall what t is. T is the denominator of sigma in this expression of sigma as a quotient of two integers, and t has been chosen to be a positive integer. So see, what we have here is the t minus 1th power of the real number c to the power 1 over t. That's what we have in the first term. Then like that, the t minus 2th power of this thing, like that, the exponent is decreasing 1 by 1, and ultimately we have, c vanishes. Simultaneously, L makes its presence more and more prominent in the sense that higher and higher powers of precisely L to the power 1 over t are coming. Okay, and eventually L is all we have. So all these powers are positive, C is positive, okay, and L is positive, that is coming from the hypothesis. The limit is assumed to be positive. So this right hand side is positive, so there is no problem with this. Okay. Now what? Now, for any integer n greater than or equal to maximum of n and k, we have n is this, starting from capital N, all the terms xn are greater than c, and starting from capital K, these things happen. So for the choice small n, like this, both these things will happen with the terms xn. So we have this. Let me start the calculation from here and let's see how neatly we can write. Xn to the power 1 over t minus L to the power 1 over t times this thing, c to the power t minus 1 divided by t plus t minus 2 divided by t times L to the power 1 over t plus etc. plus the tth root of c times this t minus 2 divided by t plus L to the power t minus 1 divided by t. Okay, so this thing is just this thing, but with that now we are multiplying this, and this is less than or equal to xn to the power 1 over t minus this. We are now going to replace all the c's with xn using this inequality, but we have to justify whether we can really do that. Let us first write the expression t minus 2 divided by t times this plus the tth root of xn times L to the power t minus 2 divided by t plus L to the power t minus 1 divided by t. Okay, so it is just this expression. We have written xn in place of c, and the justification for that comes again from Lemma 569. But which part? Part D, I think. Ideally I should have written that here, but let me just write it here. By Lemma 569 D. You just go to this and you will understand why we can. You see, what we are doing is this: c is less than xn, so we are putting these exponents, that's all. And this we can do by part D of Lemma 569 when the exponents are positive rational numbers, and they are. Okay, convince yourself that all these exponents that you see here are positive rational numbers, and then of course we are multiplying such inequalities to create these product terms. Since everything you see here, all the terms are positive real numbers, so such multiplications will preserve the direction of the inequality, and then you add those products, so you get this. And then what you are doing, you are multiplying on both sides of this inequality by this quantity, which also you can do because of the presence of absolute value. This quantity is only this much, is a non-negative real number. Now because this is positive, you can write it, the entire thing, within as an absolute value. Times and this is the tth power of the tth root of xn minus the tth power of the tth. Let me just write it explicitly. In this step, we have used that result from elementary algebra that we were talking about. Here, in place of a, we are considering the tth root of xn, and in place of b, we are considering the tth root of l. This is equal to xn minus l. But because our n has been chosen to be greater than or equal to not just k from which not just greater than or equal to n, because of which c we were able to replace c with xn, but it is also greater than or equal to k. So this is less than or equal to this. This thing is less than or equal to epsilon times c to the power whatever we have. Now look at the first term and this last term. This entire thing is less than or equal to this thing, where this factor is common, which is a positive real number. So you can cancel it from both sides. This implies and that also can be, justified by a result which is just simply that if you have a positive real number on both sides of an inequality, you can cancel that precisely by this proposition that this thing xn minus l 1 over this is less than or equal to epsilon for what type of n's? For all n greater than or equal to maximum of n and k. And this maximum itself is a positive integer. Hence, limit of the sequence xn to the power 1 over t is equal to l to the power 1 over t. So now we can apply the limit laws. So by the limit laws, limit of xn to the power sigma is equal to, by definition, because sigma is a rational number, it is this, and because of this and the limit laws, this is equal to the sth power of the tth root of l, which again is this. So we have proved the result that we were talking about. Now we will use this. Now we need ink. I have lost track of time. I don't know how long the video has been and how much longer do I have space in the recording device. If it abruptly ends in the middle, we will continue from where it ends. Now we return to our second identity from part B. I think it's better to prove parts D and E in another video. Let us not rush through this and make unwanted mistakes. Let us complete part B and stop the video. In the next part, we will prove parts D and E, and of course that will end everything with sequences. I mean, so far we have. And we will then also start infinite series. So I am cleaning this part as well. This is the kind of thing that one goes through once in life and then move on. I mean, you go through the details for once, you see that all the things work out perfectly, and then you know that yes, these laws that we have been using throughout our mathematical life, they are actually true, and then we again continue to use them as usual without thinking of the proof ever again. The result is trivially true, or the identity is trivially true when R is equal to 0. So let us now assume that R is greater than 0. There of course would also be the case where R is less than 0. We will deal with it afterwards. Since limit of Rn is equal to R and R is greater than 0, we can assume without loss of generality that the sequence Rn is positively bounded away from 0, and hence Rn is greater than 0 for all n. Recall that the sequence Rn is our choice, okay. We are getting one such sequence Rn, because R is a real number, so by definition R is the limit of a sequence of rational numbers. But now, since we have this additional assumption R is greater than 0, so we know from our previous results that we saw when we developed the theory of order, okay, in the system of rational numbers, and then in the system of rational numbers, of course, because the sequence Rn we have here is a sequence of rational numbers. So there we saw that if a real number is positive, then there exists a sequence of rational numbers converging to that real number, which is positively bounded away from 0. And a consequence of that is that all the terms of the sequence are themselves positive rational numbers. So in place of that arbitrary Rn, we can choose, if we want, such a sequence Rn which is positively bounded away, and we don't lose any generality in doing that. That's what we have here. Since x to the power q is greater than 0 by part A, we can choose a positive integer in, let us take n1 or m1, such that 1 over m1 is strictly less than x to the power q. This fact comes from the Archimedean property. We can choose this m1 sufficiently large that its reciprocal is less than x to the power q, no matter how small x to the power q is. Then 1 over m is also less than x to the power q, for all integers m greater than or equal to m1. Next, now there exists the positive integer m2 greater than or equal to m1, such that x to the power qn minus x to the power q, the distance between these two things, is less than or equal to 1 over m for all n greater than or equal to m2. What have we done here? See, x to the power q by definition is the limit of this sequence. So that's why if our epsilon is 1 over m, then this distance can be made less than or equal to that, starting from some stage, and that some stage can be chosen to be, it can, of course you can choose that stage. If you have got one such stage, then you can choose a larger such stage. Starting from that onwards also whatever you want is happening. So we can choose that m2 to itself be greater than or equal to m1. This has also been done for some necessity, for some technical reasons. Or this same thing can also be written like this, or in place of these inequalities we can write x to the power q minus 1 over m less than or equal to x to the power qn, which is less than or equal to x to the power q plus 1 over m for all n greater than or equal to m2. This implies by parts A and not A, B and D of lemma 569 that x to the power q minus 1 over m whole to the power rn is less than or equal to x to the power qn whole to the power rn, which is equal to x to the power qn rn, which is less than or equal to x to the power q plus 1 over m whole to the power rn for all n greater than or equal to m2. So what we have done here, because all the rn's are positive rational numbers, so by part D of lemma 569 we can take the rnth powers of these things, and the inequality will you will get similar inequalities like these ones. So this to the power rn is less than or equal to this to the power rn, and this is equal to this, because note that here the exponents are rational numbers and your x is a positive real number. So here we are using part B of this lemma in this step, and that again is less than or equal to this for all n greater than or equal to m2. Now by lemma 6413, which is the comparison principle, we have if you are keenly following all the steps, you must have already run into a confusion here. I am going to address that soon. Let me just write first what we have. We have x to the power q minus 1 over m whole to the power r is less than or equal to x to the power qn so because we are changing n, we will at once have qr here, and that is less than or equal to r for all m greater than or equal to m1. What happened to n? And so let us just see what we have done till this, and in fact in this step itself there is something that we have not written explicitly. You see that the epsilon we have chosen here is 1 over m, but that small m is not something fixed. That small m itself is changing. So for that value of epsilon 1 over m, we have found the stage m2. So m2 is dependent on small m, and as small m changes, m2 also will likely change, which means that whatever we have been doing here, we are doing for each such small m separately. Although the dependence of capital M2 on small m has not been explicitly mentioned. Now we are going to mention. So we instead of me blabbering on like this, let me just set things straight like what I have written here. We should perhaps stop here and see what's really going on. Note that M2 depends on small m. So when we are considering the sequences, three sequences we have considered here in these inequalities. M2 to infinity, x to the power qn rn, there also this, and each choice okay, we cannot clean this part yet because we haven't said what we have done here. No? Each such choice of small m greater than or equal to m1 possibly gives us a set of three different sequences. Okay, so the inequalities we have written here, these inequalities, there are infinitely many because n is changing, but there are sets of infinitely many inequalities, and each such set comes from a single value of m. Once you choose that small m, you get these inequalities. For a different value of m, you likely get some other inequalities which are also like this. Okay. So this far we have justified at least what we have done here. We have said that thing. However, after this, what have we done? By lemma 6.4.13, we have this. So clearly here what we are doing, we are taking limits on these inequalities. But what is the variable of our limit? That variable is n. Okay, limit of these quantities as n tends to infinity. That's the thing we have considered, and this limit by definition is this, because that is the exponent r, which is the limit of Rn as n approaches infinity. Here what is happening, Qn has the limit q, Rn has the limit r, so Qn Rn by the laws of limits, limit laws, converges to qr. So the middle limit is this one, and like that the rightmost limit is this one. But that is happening for each individual m separately. So m continues to be like that, and this is true for each such m. However, more specifically, now we are going to continue. But the even bigger question is this still recording? Yeah. Fortunately, it is still recording, so that means we still have time. What I use for recording these things is my mother's smartphone. I don't have a video camera or some such expensive things. Each choice of m greater than or equal to m1 is giving us a possibly new set of three sequences. These three sequences. Why a possibly new set? Because this capital M2 depends on small m. So every time you consider one small m, the sequences that you consider here, the terms of course are these, but the starting point likely changes. In every such set, all the three sequences are convergent. Which follows from where? From lemma 671, because here the things that are changing are the exponents. So from lemma 671 we know that all these sequences are convergent, no matter what small m is and no matter what these capital M2 stages are. Note that M2, whatever this M2 is for each small m, it has all of such M2s have been deliberately chosen to be greater than or equal to M1, so that the inequalities from where we started, keep that in mind. Those inequalities are these. No. What was it? What were those x to the power qn, these inequalities. For these inequalities, m of course starts from m1, but the n that we are choosing, that is then starting from m2. This n here. So that is why we are writing for all m greater than or equal to m1. But in spite of possibly starting from a different stage, since we already know that the limit of a convergent sequence does not depend on the first few terms, finitely many terms. So the limits are going to be the same. When you change n, no matter where these sequences start, what their terms are, the limits are this for this one, this is for this one, and this is for this one. So that's what we write next. By, and that fact we already proved in exercise 613. The first finitely many terms don't matter. And we have by the definition of real exponentiation, these are not results, these are definitions. Okay. And this is equal to the power r, right? Oh, and for what type of m? For all m greater than or equal to m1, because small m is also not fixed. Since the sequences, okay, so next we consider this. Let me write it here. Both converge to x to the power q the result that we proved in the previous paragraph implies limit of this is equal to and that is equal to okay. Now we have those inequalities that we ultimately got. I mean, we were justifying the steps here, but this is something else. These two sequences clearly converge to x to the power q because 1 over m converges to 0 no matter where m starts. So by the result we proved in the previous paragraph, that means that L result, that x to the power n xn to the power sigma converges to L to the power sigma, that result implies this. Now let us see whether we can really apply that result. In that result, what we had is a sequence of convergent sequence of positive real numbers. In place of that sequence xn, you can consider these two sequences. There is no doubt about positivity of the terms of this sequence, but what about this sequence? Recall how we considered capital M1. Capital M1 was chosen to be a positive integer such that 1 over M1 is less than x to the power q. And the small m that we are choosing starts from capital M1, so these terms are actually also positive real numbers. So the result that we proved in the previous paragraph actually is applicable here, and R is, wait, have I made a mistake here? Let me just see. According to that result, R is a positive real number. Okay. Now, according to that result, R is a positive rational number. So what we have done here is that we have taken R, of course, for us is a real number, not necessarily a rational number. Oh, so is that going to make it not work? Because whatever we are writing here, it does not make sense, no? The bases are real numbers, but the exponents we considered there are rational numbers, so we cannot use R here. We already have obtained, we have got rid of the Rn's, and we came to this stage where we have R. However, it seems that that is not enough. So either I am making a mistake here in interpreting the thing that I did sometime back, or this is a genuine mistake, and that means this thing stops here. Let me just see for a moment, okay, whether I have made a mistake or I am making a mistake in interpreting it. The result we proved in the previous paragraph shows that this limit is equal to Now this, I think this is a genuine mistake. The whole proof stops here. Okay, it's incomplete. So that means I have to complete it and then come back in the next video with a correct proof, which I don't know how I am going to do, so I will just try. Hopefully I will find it. So that means what I have to do is to prove a result analogous to the one that we proved in the previous paragraph. Namely, now our sigma needs to be a real number, not just a rational number. I think one can derive this from the result that we already have in the first paragraph, where the exponents are rational, because when we have rational exponent, you then have to continue it, and you can consider such a sequence. There you can have real exponent. Can one not take these limits and still get that thing? In these inequalities means the inequalities that we obtained before these explanations, there we have got this quantity, now x to the power qr, but we also have to get x to the power q whole to the power r, which seems to be only possible in this way. So yes, in our previous paragraph, that result needs to be strengthened to the case where sigma is a real number, not just a rational number. So with this, I end the proof in this very messy and incomplete. Already it was going to be incomplete. If we managed to prove part B, then also it would have been incomplete. But now this is even more incomplete. I need to come up with a proof of part B. You also try. I think it won't be very difficult to rectify the things and salvage the proof. Anyway, so we will see this in the next part, and tomorrow of course there is no video, but day after tomorrow on Tuesday we have graph theory. So if you want to write a comment on these things or anything else related to mathematics, you can use the comment section below, or you can mail me at my usual address. So that being said, see you on Tuesday. This is me, Lucifer, from a mathematical room. Have a nice night.